Trillions upon trillions of years from now, long after every star has burned out and every galaxy has drifted beyond sight, the universe will still be here, stretching endlessly through the darkness, carrying within it the memory of everything that ever was. It is a future so distant that our human minds can barely hold its shape, and yet it waits for us all, patient and certain, at the far edge of time. Tonight, we explore the quiet fate of everything that exists, the slow unwinding of stars, the fading of light, and the long silence that follows. It is not a story of endings alone, but a meditation on what it means for something as vast as the cosmos to gently come to rest. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will carry you through the epochs of cosmic time, from the bright age of stars to the infinite stillness that lies beyond. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever wondered what the universe looks like when all the lights go out, when the last star flickers and fades and only darkness remains? You are not alone. If these quiet cosmic journeys bring you peace, consider subscribing so you never miss the next one. Our little community grows one sleepy soul at a time. Now let your shoulders drop, let your breathing slow, and allow your thoughts to soften like distant starlight fading into the void. There is no hurry here, no urgency, only the gentle unfolding of time stretching out before you. Let us begin. The universe is approximately 13.8 billion years old, yet its story has barely begun. 13.8 billion years sounds ancient beyond imagining, yet in the grand timeline of what is to come, we are living in the earliest dawn of cosmic history, a fleeting moment when the universe is still young, still bright, still full of burning stars and swirling galaxies that will one day fade into silence. If the entire future of the cosmos were compressed into a single year, everything that has happened so far, every star that has ever shone, every civilization that has ever risen and fallen, would occupy less than the first second of that year, a mere flicker at the beginning of an unimaginably long story. The universe has been expanding and cooling since the Big Bang, but the vast majority of its existence still lies ahead, stretching forward into epochs so distant that our current era will be remembered as the time when the cosmos was still warm and full of light. We live at the bright beginning. Everything in the universe is moving away from everything else, carried by the expansion of space itself. It is not that galaxies are flying through space like ships sailing across an ocean, but rather that the fabric of space itself is stretching, carrying everything within it further apart with each passing moment, so that two galaxies that were once neighbors will eventually find themselves separated by distances so vast that light itself could never bridge the gap. Imagine dots drawn on a balloon that is slowly being inflated, each dot moving away from every other dot, not because the dots themselves are moving, but because the rubber between them is expanding, creating more space where there was none before. This expansion is happening everywhere at once, in every direction, at every scale beyond the pull of local gravity, a quiet stretching that has been going on since the universe began and will continue for as long as there is a universe at all. Space itself is growing, carrying galaxies apart like leaves floating on a rising tide. The cosmos unfolds in silence. The expansion of the universe is accelerating, driven by a mysterious force called dark energy. For billions of years, astronomers assumed that the expansion of the universe must be slowing down, gradually losing momentum as the gravity of all the matter within it pulled everything back toward itself. But in 1998, observations of distant supernovae revealed something unexpected, that the expansion is not slowing at all, but speeding up, driven by some unknown force that permeates all of space, and pushes everything apart with increasing strength. Scientists call this mysterious influence dark energy, not because they understand what it is, but because they do not, a name that acknowledges our ignorance as much as it describes the phenomenon. Dark energy makes up roughly 68% of everything in the universe, yet its nature remains one of the deepest mysteries in physics, a force that defies our intuitions and challenges our understanding of the cosmos. The universe is running away from itself, faster and faster. An invisible hand pressing the cosmos apart. In about 5 billion years, our sun will begin to die, swelling into a red giant that engulfs the inner planets. The sun that warms your face is slowly consuming its fuel, fusing hydrogen into helium in a core where temperatures reach 15 million degrees. And in roughly 5 billion years, that hydrogen will begin to run out, setting in motion a transformation that will see our familiar yellow star swell into a red giant so enormous that its outer edges will reach beyond the orbits of Mercury and Venus, perhaps even touching Earth itself. As the core contracts and heats up, the outer layers will expand outward, cooling and reddening as they go, turning the sun into a bloated giant hundreds of times larger than it is today. The oceans, the mountains, the very rocks of our planet may be vaporized or swallowed entirely, erased by the death throes of the star that once gave them life. It is a future written in the physics of stellar evolution. Our sun will one day reach out and reclaim its children. When the sun exhausts its fuel, it will shed its outer layers and become a white dwarf the size of Earth. After swelling into a red giant, the sun will gently release its outer layers, creating a beautiful planetary nebula of glowing gas that will drift outward into space. While at the center of this expanding shell, the dense core will remain, a white dwarf no larger than the Earth, yet containing most of the sun's original mass, crushed into a sphere so dense that a teaspoon of its material would weigh tons. This white dwarf will glow with residual heat at first, a faint ember left behind after fusion has ended, but over billions of years it will slowly cool, fading from white to yellow to red, and eventually to the cold darkness of a black dwarf. The sun will not explode or vanish in violence, but will simply fade, a slow and peaceful retirement, a quiet spark where once there was a blazing fire. Long before the sun dies, Earth's oceans will evaporate as our star grows hotter with age. The sun is not a constant lamp, but a slowly evolving star that grows brighter and hotter with each passing eon. And long before it swells into a red giant, perhaps in as little as 1 billion years, the increased solar radiation will begin to evaporate the oceans of Earth, sending vast quantities of water vapor into the atmosphere where it will trap even more heat, accelerating a runaway greenhouse effect that will eventually boil away every drop of liquid water on the surface. The blue planet that we know, with its vast seas and teeming life, will become a scorched and barren world, its oceans turn to steam, its skies thick with water vapor that will eventually be stripped away by the solar wind, leaving behind a dry and lifeless rock not unlike Venus. Life as we know it will have long since perished or fled to other worlds, if such an escape is possible. The cradle of humanity will become a furnace. Our home has an expiration date. The Milky Way and Andromeda galaxies are destined to collide in about 4.5 billion years. Across 2.5 million light-years of intergalactic space, the Andromeda galaxy is hurtling toward us at roughly 300 kilometers per second, drawn by the mutual gravity between our two great spirals. And in approximately 4.5 billion years, the Milky Way and Andromeda will meet in a cosmic collision that will unfold over hundreds of millions of years. Despite the violence of the word collision, very few individual stars will actually strike one another, for the distances between them are so vast that most will simply glide past, their paths bent by gravity but never touching, while the two galaxies are stretched and distorted into tidal tails of stars, and gas that sweep across the sky like brush strokes on a cosmic canvas. Eventually, after several close passes and a long dance of gravitational attraction, the two galaxies will merge into a single, larger elliptical galaxy that astronomers have already named Milkomeda, a collision measured in millions of years. And from the dance of merging galaxies, we turn now to the quiet fate of the stars themselves. Most stars in the universe will end their lives as white dwarfs, slowly cooling over trillions of years. The vast majority of stars in the cosmos, including our own sun, are not massive enough to explode in supernovae or collapse into black holes, and so they will end their lives in a far gentler fashion, shedding their outer layers and leaving behind dense, Earth-sized cores of degenerate matter that will glow with residual heat for trillions of years before finally fading into darkness. These white dwarfs are the final resting places of ordinary stars, cosmic tombstones that mark the end of fusion, but not the end of existence, quietly radiating their warmth over timescales so long that the current age of the universe is just a moment by comparison. They are supported by the quantum pressure of electrons refusing to be squeezed together, and they will persist long after the last new stars have formed, cooling embers in an endless night. The most massive stars end their lives in spectacular supernova explosions, briefly outshining entire galaxies. When stars many times more massive than our Sun exhaust the fuel in their cores, the balance between gravity pressing inward and radiation pressing outward is suddenly broken, and the star collapses upon itself in a catastrophic implosion that triggers a supernova explosion so bright that for a few weeks it can outshine all the hundreds of billions of stars in its host galaxy combined, a single point of light visible across the universe. The explosion sends shock waves ripping through space, scattering the elements forged in the star's core: carbon, oxygen, iron, gold, and all the building blocks of planets and life, seeding the cosmos with raw materials for future generations of stars. If a supernova were to occur within a few dozen light-years of Earth, the radiation would be visible in daylight, though fortunately no such candidates lurk nearby. These are the most dramatic deaths in the cosmos, a single star screaming light. After a supernova, the stellar core may collapse into a neutron star so dense that a teaspoon would weigh billions of tons. When the core of a massive star collapses during a supernova, the protons and electrons are crushed together so violently that they merge into neutrons, packing the mass of 1.5 suns into a sphere only 20 kilometers across, smaller than a city yet so dense that a single teaspoon of its material would weigh around 6 billion tons, enough to outweigh every vehicle ever built by humanity many times over. The gravity on the surface of a neutron star is so extreme that falling from a height of 1 meter would impact the surface at several million kilometers per hour, and the escape velocity is roughly half the speed of light, meaning almost nothing can leave once it has arrived. These objects spin rapidly, often hundreds of times per second, sending beams of radiation sweeping through space like cosmic lighthouses. Density beyond imagining, a star compressed to the size of a heartbeat. Some collapsing stars become black holes, regions where gravity is so strong that nothing can escape, not even light. When the most massive stars collapse at the end of their lives, sometimes the inward crush of gravity is so overwhelming that not even the quantum pressure of neutrons can halt the implosion, and the core continues to fall inward until it becomes something entirely new, a black hole, a region of space where gravity has become infinite and escape is impossible, where even light itself, the fastest thing in the universe, is trapped forever, bent back upon itself by the warping of space-time. The boundary of a black hole, called the event horizon, is not a physical surface, but a point of no return, a threshold beyond which information, matter, and energy can only flow in one direction, inward, toward a singularity where all current physics breaks down. From the outside, a black hole appears as a dark sphere, visible only by the way it bends the light of stars behind it or by the glowing disk of superheated matter spiraling toward its doom. They are the universe's ultimate prisons. Darkness made absolute and eternal. Red dwarf stars are the most common stars in the universe, and some will burn for trillions of years. The most abundant stars in the cosmos are not blazing giants like our sun, but rather small, dim red dwarfs that burn their hydrogen fuel so slowly that some of them will continue to shine for trillions of years, far longer than the current age of the universe, outlasting every other type of star by orders of magnitude. These unassuming embers fuse hydrogen at a leisurely pace in their cores, convecting material throughout their interiors so that fresh fuel is constantly mixed in, preventing the buildup of helium ash that would halt fusion in larger stars. When the universe has grown old beyond reckoning, when every sun-like star has long since burned out and faded to darkness, the red dwarfs will still be there, tiny points of warmth in an increasingly cold and empty cosmos. They are the marathon runners of the stellar world, patient flames that will outlast almost everything. The last red dwarfs will fade away roughly 100 trillion years from now, marking the end of the stellar era. 100 trillion years is a number so vast that it defies human comprehension, a span of time roughly 10,000 times longer than the current age of the universe. Yet this is how long it will take for the last, smallest red dwarf stars to exhaust their hydrogen fuel and finally flicker out, bringing to a close the era of stellar light that began shortly after the Big Bang. When that final red dwarf fades, there will be no more stars being born, for the raw material of star formation will have been used up or dispersed beyond recall, and the universe will enter a new chapter in which no new light will ever again ignite against the darkness. The sky, once filled with billions upon billions of burning suns, will hold only cooling embers and fading remnants, the end of starlight itself. The cosmos will grow forever dark. As the final embers of starlight dim, we enter a universe ruled not by fire, but by slowly cooling remnants. After the stars die, white dwarfs will continue to cool for quadrillions of years, eventually becoming black dwarfs. Once fusion has ended in the last stars and the universe has entered its long twilight, the white dwarfs that remain will continue to radiate their residual heat into the void, cooling so slowly that the process will take quadrillions of years, timescales that dwarf even the 100 trillion-year lifespan of the most patient red dwarf. These dense stellar remnants, supported by the quantum pressure of electrons packed as tightly as nature allows, will fade from white to yellow to red and eventually emit no detectable radiation at all, becoming black dwarfs, utterly dark and cold, invisible except through their gravitational pull. No black dwarfs exist yet, for the universe is far too young, but given enough time, they will become the most common objects in the cosmos, trillions of cold, silent spheres drifting through the endless night. The slow exhale of dead stars, darkness earned through patience. No black dwarfs exist yet because the universe is not old enough for any white dwarf to have fully cooled. The concept of a black dwarf, a white dwarf that has radiated away all of its residual heat and become completely cold and dark, exists only in theory, for the universe, at just under 14 billion years old, is a mere infant compared to the timescales required for even the oldest white dwarfs to cool to absolute darkness, a process that would take between 10 quadrillion and 100 quadrillion years. Every white dwarf that has ever formed is still glowing, still visible to telescopes sensitive enough to detect their faint light, because there simply has not been enough time since the first stars died for any of them to finish cooling. In a sense, black dwarfs are objects from the future, endpoints that are certain to exist, but have not yet arrived, promises written in the equations of physics, the final destination of most stars, a darkness that is still being prepared. And as you rest with these first quiet truths of cosmic ending, let them drift through you without weight. There is no need to hold onto anything here. Simply breathe and let your body settle a little deeper into stillness. Brown dwarfs, failed stars that never ignited nuclear fusion, will also cool slowly into frozen darkness. Brown dwarfs occupy a strange middle ground between the largest planets and the smallest stars, objects that accumulated enough mass to glow with heat from gravitational contraction, but never quite reached the threshold needed to ignite hydrogen fusion in their cores. And so they have been slowly cooling ever since they formed. Unlike true stars, which maintain their temperatures through nuclear reactions, brown dwarfs have no internal energy source to replenish what they lose, and so they fade steadily, their surfaces cooling from thousands of degrees to temperatures colder than the human body, becoming essentially invisible except to infrared telescopes that can detect their faint warmth. In the far future, when the last true stars have died and the universe has grown dark, these failed stars will continue their slow fade toward absolute cold, joining the black dwarfs as silent, frozen objects drifting through an empty cosmos. Stars that never quite became stars, cooling embers from birth. Neutron stars will gradually lose their heat over countless eons, becoming cold, invisible spheres drifting through space. The neutron stars that remain after massive stars explode in supernovae are born unimaginably hot, with surface temperatures of millions of degrees, spinning rapidly and emitting beams of radiation. But over thousands, millions, and eventually billions of years, they too will cool, their rotation slowing, their magnetic fields weakening, their emissions fading until they become cold, dark objects detectable only by their gravity. The timescale for neutron stars to cool completely is somewhat shorter than for white dwarfs, on the order of billions to trillions of years, because their surfaces can radiate heat efficiently through neutrino emission. Eventually, these once brilliant pulsars will become invisible relics, city-sized spheres of ultradense matter drifting silently through a universe that has grown dark and cold around them. Lighthouses that will one day go dark, spinning down into silence. The cosmic microwave background radiation, the afterglow of the Big Bang, will continue to cool and redshift until it becomes undetectable. The cosmic microwave background radiation that pervades all of space today, the faint glow left over from when the universe first became transparent to light roughly 380,000 years after the Big Bang, is already incredibly cold, just 2.7 degrees above absolute zero. Yet it will continue to cool and stretch as the universe expands, its wavelengths growing longer and longer. Shifting from microwaves to radio waves and eventually to wavelengths so enormous that no detector could register them. This ancient light will eventually become so diffuse and stretched that it will be indistinguishable from nothing at all, a final erasure of the universe's oldest memory. Future civilizations, if any exist in that distant era, will find no trace of the Big Bang written in the radiation background. The afterglow will fade completely. The first light will become the last silence. As the universe expands, galaxies beyond our local group will eventually recede faster than light, disappearing from view forever. Because the expansion of space is accelerating, distant galaxies are being carried away from us faster and faster, and there will come a time when the space between us and those distant islands of stars is expanding so rapidly that light from them can never reach us, because new space is being created between us faster than the light can cross it. This does not violate the rule that nothing can travel faster than light, because it is not the galaxies themselves that are moving through space, but space itself that is growing. carrying them beyond any possibility of contact. Over billions of years, every galaxy beyond our local group will redshift out of visibility and then out of existence as far as we are concerned, leaving us utterly alone in an observable universe that contains only our own merged remnant. The universe will become an island, surrounded by an ocean of emptiness we can never cross. Future civilizations, if any exist, may never know that other galaxies once filled the sky with 100 billion lights. If intelligent beings were to evolve far into the future, long after the accelerating expansion has carried all other galaxies beyond the cosmic horizon, they would look out at their night sky and see only the stars of their own local group, perhaps merged into a single enormous elliptical galaxy, and they would have no way of knowing that once hundreds of billions of other galaxies filled the observable universe with light and motion. The evidence would simply be gone, redshifted into invisibility, stretched beyond detection, erased by the relentless expansion of space itself. They might develop physics and cosmology, but they would have no clue about the Big Bang, no cosmic microwave background to measure, no distant galaxies to observe. Knowledge that we take for granted today would be forever beyond their reach. The universe will hide its own history, a cosmos that forgets it was ever full of light. From the fading light of distant galaxies, we now contemplate the strange era that follows the death of stars. Scientists call the current age of the universe the Stelliferous Era, the age of stars, which will last for roughly 100 trillion years. Astronomers have divided the future history of the cosmos into distinct eras based on the dominant processes that will characterize each epoch, and the era in which we currently live is called the Stelliferous Era, a name derived from the Latin for star-bearing, acknowledging that this is the time when stars fill the universe with light and heat. This era began roughly 1 million years after the Big Bang, when the first stars ignited from clouds of primordial hydrogen, and it will continue for approximately 100 trillion years, until the last red dwarfs exhaust their fuel and flicker out. 100 trillion years is an inconceivable span of time, yet even this represents only a small fraction of the universe's total future, a brief flowering of light and warmth before the long darkness that follows. We are living in the springtime of the cosmos. The summer and autumn and endless winter still await. After the Stelliferous Era ends, the universe enters the Degenerate Era, dominated by stellar remnants and black holes. Once the last stars have exhausted their fuel and faded into darkness, the universe will enter what physicists call the Degenerate Era, a vast epoch lasting perhaps from 100 trillion to 10 to the power of 40 years, dominated not by burning stars, but by the cold remnants they leave behind: white dwarfs, neutron stars, brown dwarfs, and black holes, all slowly cooling and decaying in a cosmos that has run out of new fuel for stellar generation. The word degenerate here refers not to moral decline, but to degenerate matter, the strange quantum states that support white dwarfs and neutron stars against collapse, matter in which particles are packed as tightly as the laws of physics allow. During this era, occasional flickers of light may still occur when stellar remnants collide, or when brown dwarfs capture enough mass to briefly ignite, but these will be rare exceptions in an otherwise cold and dark universe. The age of stars will have ended. The age of remnants will have begun. In the Degenerate Era, occasional collisions between stellar remnants may briefly create new stars, fleeting sparks in the darkness. Even after the raw material for new star formation has been exhausted and the last natural stars have died, the Degenerate Era will not be entirely without light, for on rare occasions, two brown dwarfs or white dwarfs may drift close enough together to merge, combining their mass in a collision that could briefly ignite nuclear fusion, creating a short-lived star that blazes for a few million years before fading once more into darkness. These chance encounters will become increasingly rare as the universe expands, but over the immense timescales of the degenerate era, they will happen many times, momentary sparks of warmth in an otherwise frozen cosmos. Any life that manages to survive into this distant future might cluster around these brief stellar flickers, harvesting what warmth they can before the inevitable darkness returns. Accidental stars in a universe that no longer makes them. Brief candles in an endless night. Planets and moons will continue to orbit their dead suns for billions of years. Frozen worlds circling cold embers. When stars die, their planets do not simply vanish, for the gravitational bonds that hold solar systems together persist even after the central fire has gone out. And so the planets and moons that once basked in starlight will continue to orbit their dead suns for billions of years. Frozen worlds circling white dwarfs or neutron stars, their surfaces locked in permanent darkness, their atmospheres frozen solid, their oceans turned to ice many kilometers deep. On some of these worlds, geothermal heat from radioactive decay might sustain liquid water beneath thick ice crusts for billions of years, but even these internal fires will eventually fade. In the end, these planets will become utterly cold and still, orbiting in perfect silence around dead stars that emit no light and no warmth, gravestones marking the positions of solar systems that once teemed with possibility. Frozen orbits around cold hearts, worlds waiting for warmth that will never return. Rogue planets ejected from their star systems will drift through the void indefinitely, carrying frozen oceans beneath their surfaces. Throughout galaxy formation, countless planets have been ejected from their birth systems by gravitational interactions, flung out into the space between stars where they drift endlessly through the void, unbound to any sun, receiving no warmth from any external source. Astronomers estimate that there may be more rogue planets in the Milky Way than there are stars, a hidden population of wanderers that we have only begun to detect because they emit almost no light of their own. Some of these nomadic worlds may be gas giants, others rocky planets like Earth, and some may carry thick ice crusts beneath which liquid water oceans persist, heated by radioactive decay in their interiors. In the far future, long after the stars have died, these vagabonds will continue their journeys through a dark and empty cosmos, worlds without suns, travelers with no destination. Some scientists speculate that life could survive around white dwarfs for trillions of years, huddled close to fading warmth. Although the death of the sun would certainly end life on Earth as we know it, some researchers have speculated that life could continue to exist around white dwarfs for trillions of years, far longer than the current age of the universe, if organisms could migrate to planets orbiting close enough to these cooling embers to receive usable warmth. A white dwarf radiates heat slowly enough that a well-positioned planet could remain habitable for an almost inconceivable span of time, potentially outlasting the entire stelliferous era by orders of magnitude, providing a refuge for any beings patient and resourceful enough to make the journey. The habitable zone around a white dwarf would be very close, perhaps only a few million kilometers from the star, and the planet would likely be tidally locked with one face permanently turned toward the warmth. But these challenges might be overcome by sufficiently advanced life forms. Survival in the twilight of the cosmos, huddling close to a dying spark. As galaxies disperse, gravitational interactions will slowly eject stars into intergalactic space, one by one. Galaxies are not static structures, but dynamic systems in constant evolution. And over immense timescales, the gravitational interactions between stars will gradually reshape them, slingshotting some stars outward into the voids between galaxies, while funneling others inward toward the central supermassive black hole. This process, called gravitational evaporation, operates over trillions of years, slowly dismantling galaxies star by star until only the dense core remains, surrounded by an ever-expanding halo of ejected stars drifting alone through intergalactic space. The stars that are ejected will continue to burn, and then to cool, and then to fade, each one becoming an isolated island of matter in a sea of expanding emptiness, too far from any other object to interact or merge or feel any gravitational tug at all. Eventually, what were once majestic spiral and elliptical galaxies will be reduced to scattered remnants, the gravitational bonds that held them together slowly dissolving into nothing. And as the galaxies scatter their stars into the void, we turn now to the patient work of gravity on cosmic scales. Over immense timescales, gravitational radiation will cause orbiting objects to slowly spiral inward, eventually merging. Einstein's theory of general relativity predicts that any two objects orbiting each other will emit gravitational waves, tiny ripples in the fabric of spacetime that carry energy away from the system. And although this effect is incredibly weak for most orbital configurations, over sufficiently long timescales, it causes even the most stable orbits to slowly decay, with the orbiting objects spiraling ever closer together until they eventually merge. For objects like the Earth orbiting the Sun, this process is utterly negligible on human timescales, but over trillions and quadrillions of years, even these stable systems will feel its effects, with planets spiraling inward to be swallowed by their dead stellar remnants or outward to escape entirely, depending on the complex gravitational interactions within the decaying system. Every bound system in the universe is slowly losing energy to these invisible waves, ticking down toward an eventual merger or ejection. Gravity decays what gravity creates, orbits spiraling toward their endings. Even the most distant objects in a galaxy will eventually fall toward the central black hole or be ejected into the void. The fate of every object within a galaxy is ultimately binary, determined by the complex gravitational dance of countless stars over inconceivable stretches of time. Some objects will gain enough energy from close encounters to be flung outward, escaping the galaxy's gravitational grip and sailing off into the emptiness between galaxies, while others will lose energy and spiral inward, eventually crossing the event horizon of the central supermassive black hole and adding their mass to its ever-growing hunger. This sorting process operates over timescales of 10 to the power of 20 years or more, slowly redistributing the contents of the galaxy until almost nothing remains in between, just a massive black hole at the center and a scattering of ejected remnants drifting through the void. The galaxy will eat itself from within while shedding its outer layers into infinity. No middle ground, only the center and the edge. Black holes will become the dominant structures in the universe, containing most of the remaining mass. As the eras progress and the stars die off, and the galaxies disperse their contents through gravitational evaporation, the supermassive black holes at their centers will become the most significant repositories of mass in the cosmos, each one containing billions of solar masses concentrated into a region from which nothing can escape, while the ejected remnants scattered through intergalactic space contain comparatively little. These black holes will continue to grow whenever matter falls into them, though such events will become increasingly rare as the universe empties out and objects drift ever further apart. For a vast span of cosmic time, from roughly 10 to the power of 40 years to 10 to the power of 100 years, black holes will be the dominant structures in the universe, the primary concentrations of mass in an otherwise nearly empty cosmos. They are patient collectors, the universe's final vaults. Supermassive black holes at the centers of galaxies will continue to grow by swallowing any matter that drifts too close. At the heart of nearly every large galaxy lies a supermassive black hole, and throughout the long future of the cosmos, these gravitational giants will continue to grow, slowly swallowing any material that wanders within their reach, whether it be a stray star, a cloud of gas, or the remains of a smaller black hole that has spiraled inward over millions of years. Each meal adds to their mass, expanding their event horizons, making them even more effective at capturing whatever passes by, though the intervals between such meals will grow longer and longer as the universe empties out and matter becomes increasingly scarce. In the active past, these black holes powered brilliant quasars visible from billions of light years away, but in the far future they will sit mostly dormant, occasionally flaring into brief activity when something happens to fall in. Growing through patience, swallowing the slow trickle of a dying universe. The largest black holes in the universe could reach masses of hundreds of billions of times that of our Sun. The most massive black holes known today already contain billions of solar masses, concentrated into regions smaller than our solar system, and over the long future of the cosmos, as they continue to swallow matter and merge with other black holes, some of them may grow to truly staggering sizes, potentially reaching hundreds of billions of solar masses, objects so massive that their event horizons would span distances comparable to the distance between the Sun and the nearest stars. These ultramassive black holes would be the largest gravitationally bound structures to ever exist, containing more mass than entire galaxies do today, sitting alone in an otherwise empty universe, their enormous gravity bending light from any source that might still exist into rings and arcs visible across vast cosmic distances. They would be the final monuments to everything that once was, repositories of a cosmos worth of matter compressed into eternal darkness, the ultimate collectors. Mass beyond imagining. Even black holes are not eternal, for they slowly evaporate through a process called Hawking radiation. For decades, black holes were thought to be truly eternal objects, cosmic dead ends from which nothing could ever escape. But in 1974, the physicist Stephen Hawking showed that the strange rules of quantum mechanics allow black holes to emit a faint glow of radiation, losing mass and energy particle by particle over unimaginably long timescales, a process now known as Hawking radiation. This means that every black hole, no matter how massive, will eventually evaporate completely, shrinking away to nothing over spans of time that dwarf even the largest numbers, leaving behind only the radiation it emitted during its slow demise. The process is so slow that a black hole the mass of our Sun would take roughly 10 to the power of 67 years to evaporate, a number so vast that the current age of the universe is like a single heartbeat by comparison. Even black holes will one day fade. Hawking radiation occurs because quantum fluctuations near the event horizon allow particles to escape, carrying away energy. The mechanism behind Hawking radiation arises from the strange behavior of empty space at the quantum level, where pairs of particles and antiparticles are constantly flickering into existence and annihilating each other in tiny fractions of a second, a phenomenon so fleeting that it normally leaves no trace. Near the event horizon of a black hole, however, these pairs can be torn apart by the extreme curvature of spacetime, with one particle falling into the black hole while the other escapes into the surrounding universe, carrying away energy that comes from the black hole's mass. Over time, this slow drip of escaping particles adds up, reducing the black hole's total mass and causing it to shrink, imperceptibly at first, but steadily over the eons, until eventually nothing remains. It is one of the most elegant predictions of theoretical physics. The void gives birth to particles. The darkness slowly empties itself. From the quantum whispers at the edge of black holes, we move deeper into the incomprehensible stretches of future time. A stellar mass black hole would take approximately 10 to the power of 67 years to evaporate completely. To truly grasp the timescale over which black holes evaporate, consider that a black hole formed from the collapse of a massive star, containing perhaps 10 solar masses, would require roughly 10 to the power of 67 years to radiate away all its mass through Hawking radiation, a number written as a 1 followed by 67 zeros, a span of time so unimaginably long that every other number we have discussed tonight amounts to nothing by comparison. If you tried to count to it at 1 number per second, you would need more time than the universe has existed, multiplied by itself trillions of times over. During this inconceivable interval, the black hole would glow ever so faintly, imperceptibly at first, gradually warming as it shrinks until in its final moments it would flare briefly and vanish entirely. Patient beyond comprehension, a death measured in eternities. A supermassive black hole, like the one at the center of the Milky Way, would take 10 to the power of 100 years to evaporate. The supermassive black hole at the center of our galaxy, known as Sagittarius A star, contains roughly 4 million solar masses, and its evaporation through Hawking radiation would require approximately 10 to the power of 100 years, a number called a googol, which is so large that writing it out would take more digits than there are atoms in the observable universe. This timescale is not merely long, but fundamentally incomprehensible, a stretch of time that makes the current age of the cosmos look like the blink of an eye. Yet even this is not the longest wait the universe will endure, for the largest black holes may take 10 to the power of 106 years or more to finally evaporate. During all this time, the universe will be almost entirely empty, dark, and cold, with only these slowly shrinking black holes serving as the last repositories of concentrated energy. A googol years of waiting, and then nothing at all. The evaporation of the last black holes marks the end of the black hole era and the beginning of the dark era. When the last and largest black holes finally radiate away their remaining mass in brief final flares of Hawking radiation, the universe will enter its ultimate phase, the dark era, a time when no structures of any significance remain, when the cosmos contains only a thin soup of scattered particles, mostly photons and electrons and positrons, drifting through an ever-expanding emptiness that stretches beyond comprehension in every direction. This transition marks the end of everything that could reasonably be called activity, for there will be no energy gradients to power any process, no concentrations of matter to interact or combine, nothing but the slow and eternal cooling of whatever particles remain. The dark era will last effectively forever, or at least for timescales so long that even the concept of time itself may lose meaning, stretching out toward an infinity that our minds cannot grasp. The universe will become stillness itself, the longest silence ever known. In the dark era, the universe will contain only scattered particles, photons, and the vast emptiness of expanding space. After the black holes have evaporated and the last flickers of concentrated energy have dispersed, the dark era will be characterized by an almost incomprehensible emptiness, a cosmos in which the average distance between any two particles may be greater than the size of the observable universe today, in which photons have been stretched to wavelengths larger than galaxies, in which nothing of any structure or complexity exists to witness the eternal stillness. The photons left over from Hawking radiation will be all that remains of the once brilliant black holes, while electrons and positrons from various decay processes will wander through the void at tremendous distances from one another, occasionally meeting and annihilating in tiny flashes of gamma radiation that represent the last possible events in a universe that has run out of things to do. This is the final state toward which all present complexity is headed, the equilibrium from which no further change can emerge. Emptiness perfected, the universe at rest. The photons remaining in the dark era will be stretched to wavelengths larger than the observable universe itself. As space continues to expand throughout the dark era, the photons that remain from Hawking radiation and other processes will be stretched along with it, their wavelengths growing longer and longer as new space is created between their crests and troughs, until eventually the wavelength of a single photon may exceed the size of what was once the observable universe, making it impossible for any conceivable detector to register its passage. These photons will carry almost no energy at all. Their frequency drops so low that they represent the faintest possible whisper of electromagnetic radiation, barely distinguishable from absolute nothing. The universe will be filled with these ghost photons, relics of a time when energy existed in concentrated forms, stretched beyond recognition by the relentless expansion of space itself. Light that has forgotten how to shine, waves longer than comprehension. Time itself may lose meaning in the dark era, as nothing will change and no events will occur to mark its passage. The very concept of time depends upon change, upon events occurring that distinguish one moment from the next, and in the dark era, when the universe has reached a state of maximum entropy and no further evolution is possible, the passage of time may become effectively meaningless, for there will be nothing to measure, nothing to remember, nothing to anticipate, only an eternal sameness stretching in all directions. Philosophers have long debated whether time can exist without events, or whether it is simply a measure of change rather than an independent feature of reality, and the dark era will be the ultimate test of these questions, an epoch in which the answer may be that time simply stops mattering at all. The universe will not end so much as become timeless, frozen in a state of perfect equilibrium from which no future is distinguishable from any past. The arrow of time dissolves, eternity without chain. Let these vast spans of time wash over you gently, like the slow turning of an ancient wheel. There is nothing you need to do, nowhere you need to be. Just breathe and let your mind rest in the quiet spaces between thoughts. The second law of thermodynamics states that entropy, the measure of disorder, must always increase in a closed system. One of the most fundamental laws of physics, the second law of thermodynamics, tells us that in any closed system, entropy, which can be understood as a measure of disorder or randomness, must always increase over time, never decrease, which means that energy will always flow from concentrated, ordered states to dispersed, disordered states, from hot to cold, from complex to simple, from useful to useless. This law governs everything from the cooling of your cup of tea to the running down of the entire cosmos, and it is why the universe inevitably moves toward a state of maximum entropy, a condition in which energy is spread so evenly across all of space that no further work can be done, no further processes can occur, no further evolution is possible. The law is not a mere tendency, but an absolute constraint, a one-way arrow built into the fabric of reality itself, pointing always toward greater disorder. The universe is running down. Order inevitably yields to chaos. The heat death of the universe is the theoretical state of maximum entropy, where no energy gradients exist to do work. The heat death of the universe is the name physicists give to the final equilibrium state toward which the cosmos is heading, a condition in which entropy has been maximized and energy has spread so uniformly throughout all of space that no temperature differences, no pressure gradients, and no chemical potentials remain to drive any process whatsoever. In this state, nothing can happen because there is no available free energy to make it happen, no way to convert one form of energy into another, no means by which complexity or activity could spontaneously arise. The name heat death is somewhat misleading, for the universe will not be hot, but extraordinarily cold, hovering just above absolute zero, yet the term captures the essence of the problem that all useful energy will have been converted into unusable heat, spread thinly across the vastness of space. Every star will have burned out. Every process will have stopped. The cosmos will have reached its final rest. At heat death, the temperature of the universe will approach absolute zero, and all activity will cease. As the universe expands and cools and approaches heat death, the temperature will fall ever closer to absolute zero, that theoretical point at which all thermal motion ceases and particles reach their minimum possible energy state, though it can never quite be reached. The cosmic microwave background radiation, which currently fills space at a temperature of about 2.7 degrees above absolute zero, will continue to cool as the universe stretches, dropping to billionths of a degree, and then trillionths, and then beyond, asymptotically approaching but never quite touching the absolute zero mark. At these temperatures, no chemical reactions can occur, no biological processes can function, no machines can operate, for there is simply no energy available to power anything at all. The universe will become a vast, cold, still ocean of nearly motionless particles, each one isolated from its neighbors by distances that grow ever larger. The deepest cold, the final stillness. Some physicists believe that quantum fluctuations could occasionally create brief sparks of order, even in the heat-death state. Even at heat-death, when the universe has reached its final equilibrium and no macroscopic processes can occur, the strange rules of quantum mechanics may permit occasional fluctuations, momentary deviations from perfect uniformity that could briefly create tiny islands of order in the vast sea of disorder, particles spontaneously arranged into complex configurations by sheer chance before dissolving back into randomness. These fluctuations would be extraordinarily rare, separated by timescales that make even the googolier lifespans of supermassive black holes seem brief. But given infinite time, some physicists argue even the most improbable configurations must eventually occur, including perhaps the spontaneous assembly of structures as complex as observers, though such scenarios raise deep paradoxes about probability and existence. Whether these fluctuations would constitute meaningful events or merely statistical noise is a question that probes the very foundations of physics. Random order in eternal disorder, sparks in an infinite night. The Big Freeze is another name for the slow cooling and expansion of the universe toward heat death. Among the various scenarios for the end of the universe, the Big Freeze is perhaps the most likely, a gradual process in which the cosmos continues to expand and cool indefinitely, the stars slowly burning out one by one, the remaining matter dispersing into the void, and the temperature dropping ever closer to absolute zero over inconceivable stretches of time until nothing remains but the cold equilibrium of heat death. Unlike more dramatic endings, the Big Freeze involves no sudden catastrophe, no tearing apart of space or collapse back to a singularity, just the slow, remorseless running down of every process and the gradual fading of every light until only darkness and cold remain. It is the ending suggested by our current understanding of dark energy and the accelerating expansion, the future that awaits if the universe continues on its present course. Not a bang, but a whisper. The cosmos slowly freezing into stillness. And from the stillness of the Big Freeze, we turn to consider alternative endings that physics allows. The Big Rip is a hypothetical scenario where dark energy grows stronger, eventually tearing apart galaxies, stars, and even atoms. In one alternative scenario for the end of the universe, the mysterious dark energy that is currently causing space to expand at an accelerating rate could continue to grow stronger over time, eventually becoming so powerful that it overwhelms the gravitational forces holding everything together, tearing apart galaxies, then stars, then planets, then molecules, and finally atoms themselves in a catastrophic unraveling of all structure called the Big Rip. This scenario depends on the nature of dark energy being of a particular type, one that becomes increasingly dominant as the universe ages rather than remaining constant. And while current observations do not strongly favor this possibility, they do not rule it out either. If the Big Rip is indeed our fate, then the universe would end not in a slow fade, but in a sudden, violent shredding of everything that exists, a final moment when the expansion of space becomes infinite, all bonds broken. Space itself torn asunder. In the Big Rip scenario, the universe would end in a final moment when space-time itself is torn asunder. If the Big Rip scenario unfolds, the end would come not gradually, but suddenly, as the ever-increasing strength of dark energy first tears galaxies away from one another, then rips apart the stars within them, then shreds the planets into clouds of debris, then pulls molecules apart into their constituent atoms, and finally tears atoms themselves into scattered particles in a cascading destruction that moves from the cosmic scale down to the subatomic in a matter of hours or minutes. In the final instant before the end, the expansion of space would become effectively infinite, meaning that the distance between any 2 points would grow to infinity in zero time, a mathematical singularity that represents the complete breakdown of spacetime itself. There would be no warning, no gradual dimming of the lights, only a sudden unraveling of everything that has ever existed, leaving behind not even the particles and photons of the Big Freeze. A violent ending written in the expansion of space. The Big Crunch is the opposite scenario, where gravity eventually reverses the expansion and collapses everything back to a singularity. Before the discovery that the expansion of the universe is accelerating, many cosmologists believed that gravity might eventually halt and reverse the outward motion of galaxies, pulling everything back together in a vast contraction that would mirror the original expansion, compressing all matter and energy into an ever smaller volume until the entire cosmos collapsed back into a singularity not unlike the one from which the Big Bang emerged, ending the universe in a titanic implosion called the Big Crunch. In this scenario, the sky would gradually fill with light as distant galaxies approached and blue-shifted. Temperatures would rise as space compressed, and eventually everything would merge into a single point of infinite density, perhaps to be reborn in a new Big Bang, or perhaps simply to cease existing altogether. The Big Crunch represented a kind of cosmic symmetry, a universe that began in fire and ended in fire. A return to the beginning. Current observations suggest the Big Crunch is unlikely, as the expansion of the universe is accelerating rather than slowing. The discovery in 1998 that the expansion of the universe is accelerating rather than slowing down effectively ruled out the Big Crunch as our likely fate. For the dark energy driving this acceleration appears to be pushing galaxies apart faster and faster, overwhelming the gravitational attraction that would be needed to pull everything back together, sending the cosmos toward an ever more spread out and isolated future rather than a dramatic collapse. If dark energy remains constant or grows stronger, as current evidence suggests, then the expansion will continue forever, and no reverse Big Bang will ever occur, no grand implosion to bookend the original explosion. The universe appears to be headed not for fire, but for ice, not for a climactic ending, but for an eternal fading. The Big Crunch remains a theoretical possibility should our understanding prove incomplete. For now, infinity stretches ahead. The Big Bounce theory suggests the universe could collapse and then rebound in a new Big Bang, cycling eternally. Some cosmologists have proposed that the universe might not simply end after a big crunch, but could instead bounce back, with the compression of all matter and energy triggering a new Big Bang that would begin the cycle anew, leading to an eternally oscillating cosmos that has been expanding and contracting forever, with no true beginning and no true end, just an endless sequence of cosmic heartbeats stretching into both past and future infinity. This big bounce scenario is appealing in its symmetry, avoiding the troublesome question of what came before the Big Bang by suggesting that there was always a previous cycle, always another universe collapsing to give birth to the next. However, current physics makes it difficult to understand how the bounce itself would work, how the collapse could reverse into expansion without simply forming a singularity where all physics breaks down. A cosmos that breathes, endless cycles of birth and death. Some cosmologists propose that our universe is one of many, each born from the collapse or quantum fluctuation of another. The possibility that our universe is not alone, but merely one among countless others, each born from the collapse of a predecessor or from random quantum fluctuations in some larger space, has captured the imagination of physicists seeking to explain why our cosmos has the particular properties it does. For if many universes exist with different physical constants, then it is no surprise that we find ourselves in one compatible with life. These multiverse theories come in many varieties, some suggesting that new universes bud off from black holes, others proposing that quantum fluctuations during cosmic inflation spawn endless pocket universes, and still others imagining that every quantum measurement splits reality into branching paths, each one a universe unto itself. While these ideas remain speculative and perhaps forever untestable, they offer a framework in which the end of our universe need not be the end of everything. New worlds may be born as old ones die, creation without limits. The multiverse hypothesis suggests that while our universe may end, new universes could be born indefinitely. If the multiverse hypothesis is correct, then the death of our particular universe would not represent the end of existence itself, but merely the end of one chapter in an infinitely larger story. For new universes would continue to arise through whatever mechanism creates them, whether through the quantum birth of bubble universes in eternally inflating space, or through some other process we cannot yet imagine. Each of these new universes might have different physical laws, different numbers of dimensions, different fundamental particles, most of them perhaps lifeless and empty, but some perhaps as rich and complex as our own, each one unfolding its own cosmic drama in complete isolation from all the others. The multiverse offers a kind of cosmic immortality, not for any individual universe or any individual being, but for existence itself, for the ongoing process of creation and destruction that may never cease. Our ending may be someone else's beginning, infinity creating infinities. From the branching possibilities of many universes, we return now to the certain fate of matter itself. Protons, the building blocks of atoms, may not be stable forever, with some theories predicting they will decay over vast timescales. The protons that make up the nuclei of every atom in your body, in the Earth, in the stars, have been assumed for most of the history of physics to be absolutely stable, lasting forever unless struck by something energetic enough to scatter them apart. But some theories of particle physics, particularly those seeking to unify the fundamental forces, predict that protons are not truly eternal, but will eventually decay into lighter particles over timescales so long that no experiment has ever detected such a decay occurring. The predicted half-life of a proton is at least 10 to the power of 34 years, which means that a single proton has only a vanishingly small chance of decaying in any given year. But over timescales of 10 to the power of 40 years or more, even the most stable-seeming matter will crumble away, leaving behind only radiation and the lightest possible particles. If protons decay, then all ordinary matter is doomed. The building blocks themselves will eventually dissolve. If protons decay, all ordinary matter will eventually dissolve into radiation, leaving nothing solid behind. Should proton decay occur as some theories predict, then over spans of time measured in at least 10 to the power of 34 years, every atom in the universe will gradually fall apart, shedding its protons one by one until nothing solid remains. No white dwarfs, no neutron stars, no black dwarfs, no rogue planets. Nothing but the radiation released by the decay process and whatever other particles are too fundamental to decay any further. This means that even if the universe somehow managed to preserve solid matter through all the other processes we have discussed, proton decay would eventually erase it all, turning every stone, every planet, every remnant of every star into a thin mist of photons and electrons and neutrinos drifting through the void. The very concept of solid matter would become a thing of the past, a temporary phase in the history of the cosmos. Atoms with an expiration date. Solidity as a passing illusion. The half-life of proton decay, if it occurs, is estimated to be at least 10 to the power of 34 years. Experiments searching for proton decay have watched vast tanks of water for any sign of a proton spontaneously transforming into lighter particles, and so far none have found any evidence that this process occurs, allowing physicists to set a lower limit on the proton half-life of at least 10 to the power of 34 years, a number so large that even if you watched a single proton for the entire current age of the universe, the odds of seeing it decay would be roughly 1 in a trillion. This does not mean protons are truly stable, only that if they do decay, the process is incredibly slow, operating over timescales that dwarf even the googolier evaporation times of supermassive black holes. The search continues in underground laboratories around the world, watching and waiting for a single flash of light that would signal the death of a proton. Patience measured in decades, waiting for a single atom to blink. Without protons, there can be no atoms, no molecules, no chemistry, and no possibility of complex structures. Protons are essential to the existence of atoms, for they define which element an atom is and provide the positive charge that binds electrons into the structures we call chemistry. And without protons, there can be no atoms, no molecules, no crystals, no liquids, no gases, no solid matter of any kind, and therefore no possibility of the complex structures that we associate with existence. No planets, no life, no machines, no observers to witness the emptiness. If proton decay is real, then eventually the universe will contain nothing that we would recognize as matter, only a thin soup of radiation and the lightest possible particles, drifting through an emptiness that can never again produce anything solid or complex. Chemistry will become impossible, and with it, any form of structure or organization that depends on the binding of atoms. The universe will lose the ability to create. Complexity will become impossible. Even if protons are stable, black holes will still erase all information about the matter they consume. One of the deepest puzzles in theoretical physics concerns what happens to the information encoded in matter that falls into a black hole. For according to classical general relativity, this information is simply erased, lost forever behind the event horizon, while quantum mechanics demands that information can never truly be destroyed, but must always be preserved in some form. If black holes do erase information permanently, as Hawking originally proposed, then even if protons never decay, the matter they compose will eventually be swallowed by black holes and transformed into formless Hawking radiation that contains no trace of what fell in, no memory of whether it was a star or a planet or a library full of books. The history of everything that ever existed would be obliterated, converted into identical photons distinguishable from one another only by their wavelengths. Every story would be forgotten. The universe would become a blank page. The information paradox asks whether the information swallowed by black holes is truly lost or somehow preserved. The black hole information paradox has troubled physicists for decades, for it sets two of our most fundamental theories against each other: general relativity, which suggests that information is lost when matter crosses the event horizon, and quantum mechanics, which insists that information is always conserved, that the universe never truly forgets. If information is lost, then quantum mechanics must be modified in ways that challenge its foundations. But if information is somehow preserved, then we must understand how it escapes from behind the event horizon, either encoded in subtle correlations in the Hawking radiation, or stored on the surface of the black hole in some way we do not yet understand. The debate has driven some of the most important developments in theoretical physics over the past 50 years. The resolution may change our understanding of space and time. Whether the universe remembers or forgets remains uncertain. Some physicists believe that information is encoded on the surface of black holes and released during Hawking evaporation. One possible resolution to the information paradox suggests that the information about everything that falls into a black hole is not lost at all, but is instead encoded on the event horizon itself, stored in a two-dimensional pattern on the boundary that completely describes the three-dimensional interior, an idea known as the holographic principle. According to this view, when a black hole evaporates through Hawking radiation, the information is slowly released back into the universe, encoded in subtle correlations between the particles of radiation in a way that is extraordinarily difficult to decode, but not in principle impossible. If this is correct, then black holes are not information destroyers, but information processors, scrambling everything that enters them into an almost but not quite irretrievable form. The cosmos may remember everything after all, nothing truly forgotten, only transformed. As we contemplate the preservation or loss of cosmic information, we consider what traces of existence might endure. In the far future, there may be no witnesses to remember that stars once burned or that life once flourished. As the eras progress and the stars die out, and the black holes evaporate, and the last particles drift ever further apart, there may come a time when nothing remains that could be called a witness, no conscious mind to remember that the universe was once filled with light and warmth and life, no record of the fact that intelligent beings once existed who wondered about the cosmos and their place within it. The very memory of existence could be erased along with existence itself, leaving behind only the cold, empty, eternal darkness of the dark era in which nothing happens because there is nothing left to happen to. Whether this prospect fills you with existential dread or a strange kind of peace may depend on your philosophy, but either way, it appears to be the likely fate of everything we have ever known. Witnesses fading with what they witnessed, memory dissolving into silence. The Voyager spacecraft, now drifting in interstellar space, will continue their journey for billions of years unless destroyed by collision. The two Voyager spacecraft launched in 1977 have now left the influence of our Sun and are sailing through interstellar space at speeds of roughly 17 kilometers per second. And unless they happen to collide with something, which is extraordinarily unlikely given the vast emptiness between stars, they will continue their silent journeys for billions of years, carrying their golden records with images and sounds from Earth past stars that have not yet formed and toward destinations that no one will ever know. These small machines, built with the technology of the 1970s, may outlast every structure ever built by humanity on Earth, every city and monument and mountain, drifting on through the darkness long after our sun has died and our solar system has dispersed into the void. They carry greetings in 55 languages and music from around the world, messages in bottles thrown into the cosmic ocean with almost no hope of ever being found. Humanity's longest letters, drifting toward forever. Human artifacts on the moon may survive for millions of years, protected from erosion by the airless environment. On the surface of the moon, protected by the absence of atmosphere, weather, and biological decay, the artifacts left behind by the Apollo astronauts, the footprints pressed into the gray dust, the flags planted to mark the achievement, the lunar modules that served as homes for a few days, may survive for millions of years, virtually unchanged, a museum of human achievement preserved in the vacuum of space. Without wind or rain or microbes to break them down, these objects will slowly accumulate a thin layer of micrometeorite dust and be gently weathered by cosmic rays and the solar wind. But the process is so slow that recognizable traces may persist for timescales that dwarf the entire history of human civilization. Even after Earth has been transformed by the dying sun, these silent monuments may still be waiting on the lunar surface, testimony to a species that once reached out beyond its home world. Footprints that may outlast their makers, silent witnesses on a silent world. Radio signals from Earth are traveling outward at the speed of light, carrying traces of our civilization into the cosmos. For roughly a century, Earth has been unintentionally broadcasting its presence into the cosmos, leaking radio waves from television transmitters, radar stations, and countless other sources that spread outward at the speed of light in an ever-expanding bubble that now encompasses thousands of nearby stars and will eventually reach the far corners of the Milky Way and beyond. These signals carry fragments of our culture, our music, our conversations, our existence, diluted by distance into whispers so faint that detecting them would require technology far beyond our own. Yet they are there, rippling outward through the dark, testimony to the fact that on one small planet around one ordinary star, a species arose that filled the electromagnetic spectrum with its chatter. Right now, as you lie here, signals from decades ago are washing over distant worlds that have never been visited or even named. Our electromagnetic footprint, spreading at the speed of light. Even our radio signals will eventually become too faint to detect, scattered and absorbed by the interstellar medium. Although our radio signals are spreading outward at the speed of light, they are also growing fainter with each passing light year, diluted by the inverse square law until they become indistinguishable from the background noise of the universe, absorbed and scattered by the thin gas and dust of the interstellar medium until effectively nothing remains. Within a few hundred light years, even the most powerful transmissions from Earth would be almost impossible to detect without improbably sensitive equipment, pointed in exactly the right direction at exactly the right time. And over the millions and billions of years to come, these faint whispers will fade into the cosmic static until no trace of them can ever be recovered. Our electromagnetic legacy is not eternal, but merely very long-lived, a brief shout that echoes through the galaxy for a while before dissolving into silence, signals that fade with distance, voices growing quieter with every passing moment. The end of the universe does not mean the end of physics, for the laws of nature will continue to govern whatever remains. Even after all the stars have died and all the black holes have evaporated, and the universe has entered its final state of cold, dark equilibrium, the laws of physics will presumably continue to operate exactly as they always have, governing the behavior of whatever particles remain, dictating the probabilities of quantum fluctuations, shaping the geometry of spacetime itself, even if there is nothing interesting left for them to act upon. The equations will not change simply because the solutions have become trivial. The rules will not expire simply because the game has effectively ended. And in this sense, physics is more fundamental than any particular configuration of matter or energy that happens to exist at any given time. The universe may run down, but the laws that describe the running down will persist forever. Physics outlasts everything it describes. The rules remain even when the players are gone. As these truths of cosmic endurance settle around you, allow your body to release any tension it has been holding. Feel the weight of your limbs against the bed, the gentle rhythm of your breath, and let yourself drift a little closer to sleep. Time dilation near massive objects means that clocks run slower, and near black holes, time nearly stops for outside observers. Einstein's theory of relativity revealed that time is not a constant that flows uniformly throughout the universe, but rather a flexible quantity that depends on motion and gravity, running more slowly in regions of intense gravitational fields, so that a clock near a massive object will tick more slowly than an identical clock far away, and near the event horizon of a black hole, where gravity reaches its most extreme values, time slows to a crawl, nearly stopping altogether from the perspective of an outside observer. If you were to watch someone falling toward a black hole from a safe distance, you would see them approach the event horizon ever more slowly, their movements stretching out in time, the light from their body shifting to longer and longer wavelengths, until they appeared to freeze at the very edge of darkness, never quite crossing over, though from their perspective, the crossing would happen in an instant. Time bends near the heaviest objects. The deepest gravity holds the slowest clocks. For an observer falling into a black hole, the rest of the universe would appear to speed up, experiencing the end of time in moments. If you were the one falling into a black hole, your experience would be radically different from that of an outside observer. For while to them your descent would appear to stretch out toward infinity, to you the fall would proceed normally, your clock ticking at its usual rate. Yet as you looked back at the universe you were leaving, you would see time outside speeding up, the stars burning through their fuel in accelerated time lapse. The entire future of the cosmos playing out in the brief moments before you crossed the event horizon. Some theories suggest that a falling observer might witness billions of years passing outside in the final seconds of their descent, watching the end of stars and the evaporation of black holes compressed into a flash of accelerated time, though whether this would actually be visible or simply calculated depends on complex relativistic effects that remain the subject of debate. Falling toward the end. Watching eternity in an instant. The arrow of time, pointing from past to future, is connected to the increase of entropy in the universe. We experience time as flowing in one direction, from past to future, from memories to anticipation, from cause to effect, and physicists believe this arrow of time is intimately connected to the second law of thermodynamics and the increase of entropy, for it is the growth of disorder that distinguishes the future from the past, that makes broken eggs impossible to unbreak and melted ice impossible to unmelt, that gives time its direction and meaning. In a universe at maximum entropy, where no further increase is possible, the distinction between past and future would effectively disappear, for there would be no processes to mark the passage of time, no changes to remember or predict, only an eternal sameness stretching in all directions. The arrow of time would have nowhere to point. We experience time because the universe began in an improbably ordered state and has been running down ever since. The arrow exists because entropy grows. At heat death, when entropy is maximized, the distinction between past and future may become meaningless. In the ultimate state of heat death, when the universe has reached its maximum possible entropy and no further evolution can occur, the very concept of time, as we understand it, may lose all meaning, for there will be no processes to distinguish one moment from the next, no changes to remember or anticipate, no sense in which the future differs from the past. Philosophical debates about whether time could exist without change would find their ultimate test in this final state, where the equations of physics would still contain a time variable, but nothing in the actual universe would correspond to it in any meaningful way. Some physicists describe this as a state of timelessness, not in the sense that time stops, but in the sense that it becomes irrelevant, an unused variable in equations that describe nothing but perfect, unchanging equilibrium. Time without events. A variable without a roles. Some philosophers argue that time is an illusion, and that past, present, and future all exist simultaneously in a block universe. While we experience time as a flow from past through present to future, with each moment replacing the last in an endless succession, some philosophers and physicists have argued that this experience is an illusion, and that in reality all moments of time exist simultaneously, frozen together in a four-dimensional block universe where past, present, and future are equally real, equally present, equally fixed. In this view, the year of your birth and the year of your death are both simply locations in the block, no more separated in any objective sense than two cities on a map, and our sense of moving through time is merely a feature of our consciousness rather than a feature of reality itself. If the block universe view is correct, then in some sense the end of the universe already exists, coexisting with the Big Bang, and with this very moment, all of cosmic history laid out in a single unchanging structure. All moments existing at once, time as a place rather than a journey. And from the philosophy of time, we turn now to the strange possibilities that quantum physics allows. Quantum tunneling allows particles to pass through barriers that should be impossible to cross, given enough time. In the strange world of quantum mechanics, particles do not have definite positions until they are measured but exist in a fuzzy state of probabilities, and this allows them to do things that classical physics would forbid, such as passing through barriers that should be impenetrable, a phenomenon called quantum tunneling. When a particle encounters a barrier, there is a small probability that it will simply appear on the other side, having tunneled through in a way that defies our everyday intuitions about how objects should behave. And although this probability is usually vanishingly small for large objects, over sufficiently long timescales, even the most improbable tunneling events become inevitable. Given enough time, a rock could theoretically tunnel through a wall, a planet could tunnel out of its orbit, or the particles in a white dwarf could spontaneously rearrange themselves into entirely different configurations. Patience makes the impossible possible, probability stretched across eternity. Over unimaginably long timescales, quantum tunneling could cause iron stars to form from the random assembly of nuclei. In the inconceivably distant future, when the universe has grown old beyond all recognition and only stellar remnants remain, quantum tunneling could gradually transform the matter in white dwarfs and neutron stars into their most stable possible configuration, a form of matter composed entirely of iron nuclei, the endpoint of nuclear stability where no further energy can be released through fusion or fission. This process would take somewhere around 10 to the power of 1,500 years, a number so large that it contains more digits than there are atoms in the observable universe. Yet given infinite time, it is essentially certain to occur, with each particle slowly tunneling toward the lowest energy state available. These hypothetical iron stars would be the ultimate fate of matter itself, objects so stable that no further change is possible except through even more improbable processes that would take even longer, the slowest transformation imaginable, matter perfecting itself. An iron star would be the most stable possible configuration of matter, and it would simply sit there, unchanging, for eternity. If iron stars ever form through the unimaginably slow process of quantum tunneling, they would represent the final stable state of ordinary matter, objects from which no further energy could be extracted, around which no further evolution could occur, that would simply exist, unchanging, for all of eternity, or at least until some even more improbable quantum process caused them to slowly evaporate or collapse. An iron star would be the cosmic equivalent of a perfectly balanced object at the bottom of a valley, with no tendency to roll in any direction, no unstable energy waiting to be released, nothing left to happen. In a universe already deep in the dark era, already stripped of all other activity, these iron spheres would be the last complex objects to exist, silent monuments to the patient work of quantum mechanics over spans of time that beggar all imagination. Perfect stability achieved. The end of all change. Even iron stars would eventually collapse into black holes through quantum tunneling over timescales beyond comprehension. Even the perfectly stable iron stars, having reached the lowest energy configuration possible for ordinary matter, are not truly eternal, for quantum tunneling makes it possible for their mass to slowly concentrate, fluctuation by fluctuation, until eventually it crosses the threshold required to form a black hole, collapsing into a singularity from which not even the stable iron nuclei can escape. The timescale for this process is estimated to be around 10 to the power of 10 to the power of 76 years, a number so incomprehensibly vast that writing it out would require more digits than could fit in any book or any computer. Yet over infinite time, it is virtually certain to happen to every iron star, transforming the last stable matter in the universe into black holes that will themselves then evaporate through Hawking radiation. There is no permanent refuge. Even perfection eventually falls. A Boltzmann brain is a hypothetical self-aware entity that could arise from random quantum fluctuations in the void. In an eternally expanding universe, where quantum fluctuations occasionally create ordered structures from the void, some physicists have suggested that over sufficiently long timescales, fluctuations could spontaneously assemble something as complex as a brain, complete with memories and consciousness, floating briefly in the emptiness before dissolving back into disorder, a hypothetical entity known as a Boltzmann brain. These bizarre constructs would have no evolutionary history, no body, no external world to perceive, only the momentary flicker of self-awareness created by pure chance from the random jostling of particles in a sea of maximum entropy. The probability of such a fluctuation is unimaginably small, but over infinite time in a universe with infinite opportunities, even the vanishingly improbable must eventually occur. Whether such entities could be said to truly exist or truly think remains a deep philosophical puzzle. Consciousness from chaos, minds arising from nothing. Some physicists argue that Boltzmann brains are more likely than evolved observers, raising paradoxes about the nature of consciousness. If the universe lasts forever and Boltzmann brains are possible, then over eternal time, the number of momentary conscious fluctuations arising from random quantum processes would vastly exceed the number of observers who evolved naturally through billions of years of cosmic and biological history, which raises the disturbing question of why we should believe ourselves to be natural observers rather than Boltzmann brains with false memories of a universe that never existed. This apparent paradox has troubled physicists because it seems to undermine our ability to trust any observation or memory, yet it also suggests that there may be something wrong with our understanding of cosmology or consciousness that produces such conclusions. Various resolutions have been proposed, from limits on the future lifetime of the universe to new understanding of what consciousness requires. Whether we are real or dreamed remains an open question, the deepest puzzle of identity. The vacuum of space may not be the lowest energy state, and a true vacuum could nucleate and expand, destroying everything. The empty space that surrounds us may not be as empty or as stable as we imagine, for according to some theories of particle physics, the vacuum we live in could be a false vacuum, a metastable state that is not truly the lowest possible energy configuration, which means that somewhere, at any time, a bubble of true vacuum could spontaneously nucleate through quantum fluctuation, a bubble in which the laws of physics are different and which would expand outward at the speed of light, converting our familiar false vacuum into something utterly different as it goes. This process, called vacuum decay, would be instantaneous and undetectable, for we would have no warning of the bubble's approach, no way to stop it or escape it, no possibility of survival. The bubble would simply arrive, and everything we know would cease to exist in a single flash of transformation. The void may be unstable. Our existence may rest on borrowed time. From the fragility of our vacuum, we consider the ultimate limits of what the universe allows. Vacuum decay would create a bubble of true vacuum expanding at the speed of light, erasing space-time as it goes. If vacuum decay were to occur, a bubble of true vacuum would form at some random point in space and immediately begin expanding at the speed of light, converting the false vacuum ahead of it into the new, lower energy state as it goes, rewriting the laws of physics across a region that grows larger with every passing moment, until eventually it encompasses the entire observable universe and beyond. Inside the bubble, particles would have different masses, forces would have different strengths, and atoms as we know them might not be possible, meaning that everything we recognize as matter would be transformed or destroyed at the moment of contact. The bubble would arrive without warning, for no signal could outpace it, and whatever survived on the inside would bear no resemblance to the universe we know. It would be the most complete destruction possible, a wall of physics rewriting reality. Inside a vacuum decay bubble, the laws of physics could be completely different, incompatible with atoms or life. Within a bubble of true vacuum, the fundamental constants that determine how particles interact and how forces behave could take on entirely different values that might not permit the kind of chemistry that makes atoms stable or molecules complex, that might not allow stars to form or life to exist, that might produce a universe utterly alien to everything we know. The Higgs field, the electromagnetic force, the strong nuclear force, all could be different inside the bubble, reconfigured according to whatever the true ground state of the quantum fields turns out to be. Physicists cannot currently predict what conditions would prevail inside such a bubble, for we do not know whether our vacuum is false or what the true vacuum would look like if it exists. A universe incompatible with our existence, physics rewritten from the foundations. We would have no warning of vacuum decay, as the bubble would arrive at the same moment as any signal announcing it. One of the most unsettling aspects of vacuum decay is that there would be absolutely no warning of its approach, for the bubble expands at the speed of light, which means that any signal announcing its existence, whether light or gravitational waves or anything else, would travel at exactly the same speed as the bubble itself, arriving at the same moment, or more precisely, being overtaken by the bubble before it could possibly be detected. One moment everything would be normal, and the next moment we would simply cease to exist, transformed along with everything around us into whatever the new vacuum produces. There would be no time to react, no time to understand what was happening, no last moment of awareness before the end. It would be instantaneous and total, the most sudden ending possible. We would never know it happened. The Higgs field, which gives particles their mass, could be in a metastable state, vulnerable to quantum decay. The Higgs field that pervades all of space and gives particles their mass may be in a metastable state, balanced precariously between the current configuration that allows atoms and chemistry and life to exist, and a lower energy state that would be utterly different and almost certainly incompatible with anything we would recognize. Measurements of the Higgs boson discovered at the Large Hadron Collider in 2012 suggest that our vacuum is indeed possibly metastable, hovering in a local minimum of energy that could transition to the true minimum if given a sufficient nudge by a high-energy event or a random quantum fluctuation. Whether this actually describes our reality remains uncertain, for the calculations depend on precise measurements of particle masses that we may not yet have determined accurately enough. The field that gives us solidity may itself be unstable. Mass itself may be temporary. If the Higgs field decayed to a lower energy state, the mass of all particles would change, and matter, as we know it, would cease to exist. If the Higgs field were to decay to a lower energy state, the consequences would be catastrophic and total, for the masses of all fundamental particles, the electrons, the quarks, everything from which matter is built, would suddenly change to new values determined by the new vacuum configuration, values that would almost certainly not permit the existence of stable atoms or the chemistry that depends upon them. Protons might become unstable or simply cease to exist. Electrons might become too heavy or too light to form proper atomic orbitals, and the entire periodic table of elements that makes existence possible would simply vanish, replaced by whatever the new physics allows. It would not merely be the end of life, but the end of matter itself, a transformation so complete that nothing recognizable would survive. The foundations of everything would shift. Existence would be redefined. The probability of vacuum decay is so low that it may never happen, even over the lifetime of the universe. Despite the alarming implications of vacuum decay, the probability of such an event occurring anywhere in our observable universe is extraordinarily low, so low that it may never happen at all, even over timescales that dwarf the current age of the cosmos by factors of billions upon billions. The metastability of our vacuum, if it exists, is so deep and the barrier to transition so high that random quantum fluctuations capable of triggering the decay are almost inconceivably rare, and no known natural process is energetic enough to provide the necessary nudge. The fact that the universe has existed for nearly 14 billion years without such a transition is itself evidence that the probability is very, very small. We may well live out the entire future history of the cosmos without ever experiencing vacuum decay. The danger may exist forever without ever becoming real. Safety found in improbability. And as we ponder these ultimate catastrophes, we also consider the possibility that the end is not truly the end. Conformal cyclic cosmology proposes that the universe cycles through endless eons, each Big Bang emerging from the death of the last. The physicist Roger Penrose has proposed a model called conformal cyclic cosmology, in which the universe does not simply end in heat death, but rather transitions into a new eon, a new cycle of cosmic history that begins with what appears to be a new Big Bang emerging from the infinite expansion and cooling of the previous cycle. In this model, as the universe expands forever and all massive particles decay away, leaving only radiation stretching across an increasingly empty space, the very concept of scale becomes meaningless, and the infinite future of one eon becomes mathematically identical to the tiny, hot singularity of the next, creating an eternal sequence of cosmic cycles with no true beginning and no true end. If Penrose is correct, then our Big Bang was simply the death of a previous universe, and our eventual heat death will become the birth of another, endings becoming beginnings, time folded into eternal recurrence. In this model, the infinite expansion of one eon becomes indistinguishable from the singularity of the next. The key insight of conformal cyclic cosmology is that in a universe containing only massless particles like photons, the distinction between very large and very small becomes meaningless. For without massive particles to define a scale, there is no way to measure distance or time in any absolute sense, and the infinitely expanded, infinitely cold future of one eon is mathematically indistinguishable from the infinitely small, infinitely hot singularity of another. This conformal equivalence, as mathematicians call it, means that the boundary of one cycle can be smoothly joined to the beginning of the next, creating a continuous, eternal universe that cycles endlessly without ever truly ending or beginning. The model remains speculative, for we cannot be certain that all massive particles will eventually decay or that the conformal matching works exactly, but it offers a beautiful vision of cosmic eternity, infinity and zero becoming one. The end touching the beginning. Some cosmologists search for circular patterns in the cosmic microwave background as evidence of previous eons. If conformal cyclic cosmology is correct, then events from previous eons might leave subtle imprints on our cosmic microwave background radiation, patterns and anomalies that could not have arisen from processes within our own cosmic history, but which carry information across the boundary between cycles, whispers from a universe that died to give birth to our own. Penrose and his collaborators have claimed to find evidence for such patterns, concentric circles of unusual temperature uniformity that they interpret as the signatures of colliding black holes in the previous eon, though other cosmologists have disputed these findings, arguing that the patterns can be explained by statistical fluctuations or instrumental effects. The search continues, for if we could confirm evidence of a previous eon, it would be among the most profound discoveries in the history of science. Echoes from before the beginning, messages from a previous existence. The ekpyrotic model suggests our universe was created by the collision of higher dimensional membranes, which could happen again. According to some theories inspired by string theory, our universe exists on a three-dimensional membrane, or brane, floating in a higher dimensional space, and the Big Bang may have been triggered by a collision with another brane, a cosmic crash that released enormous energy and set our universe expanding from what appeared to be a singularity, but was actually a moment of contact between two higher dimensional surfaces. In this ekpyrotic model, named after the ancient Greek concept of the universe being periodically consumed and reborn by fire, such collisions could happen again, perhaps creating new Big Bangs within our universe or spawning entirely new universes in the higher dimensional bulk. The model remains highly speculative, for we have no direct evidence of extra dimensions or of the branes themselves. A collision that created everything, perhaps waiting to happen again. String theory allows for landscapes of possible universes, each with different physical constants and laws. String theory, the leading candidate for a theory of everything that might unite quantum mechanics with gravity, predicts not a single unique universe, but a vast landscape of possible universes, perhaps as many as 10 to the power of 500 different configurations, each one with different values of the fundamental constants, different numbers of dimensions, different particle types and forces and laws of nature. In this landscape, our universe with its particular constants tuned to allow chemistry and stars and life is merely one possibility among an almost inconceivable number, and other configurations, most of them lifeless and strange, may exist as separate bubble universes in an eternally inflating multiverse. If this picture is correct, then the end of our particular universe is merely a local event in a far vaster cosmic story, one ending among countless others. Different universes with different fates. In an eternally inflating multiverse, new pocket universes are constantly being born, even as old ones die. According to eternal inflation theory, the rapid expansion that occurred in the first fraction of a second after the Big Bang never truly stopped, but continues even now in regions beyond our observable universe, constantly spawning new pocket universes that bubble off from the inflating background like droplets forming in an endless ocean, each one potentially with its own Big Bang, its own physical laws, its own cosmic history. In this picture, while our universe may eventually reach heat death or suffer some other fate, the process of universe creation continues forever, with new pockets constantly being born to take the place of those that grow old and die, an endless proliferation of realities stretching into eternity. Our ending would not be the ending. New universes forever being born, creation that never ceases. The anthropic principle suggests we find ourselves in a universe compatible with life, because only such universes can be observed. The anthropic principle offers a simple yet profound explanation for why the universe appears so finely tuned for life, with physical constants that fall within the narrow ranges needed for atoms to be stable, for stars to burn long enough for planets to form, for chemistry to produce the complexity that we call biology. If many universes exist with different constants, as the multiverse hypothesis suggests, then it is no surprise that we find ourselves in one of the rare configurations compatible with observers, for by definition, we could not exist in any of the others, and so our observations are necessarily biased toward universes where observation is possible. This does not explain why the universe exists at all, but it does explain why it has the particular properties it does. We see what we can see. Our existence selects the universe we inhabit. Allow these vast cosmic cycles to carry you gently, like waves in an endless ocean of time. Let your thoughts soften and scatter, and feel your body growing heavier and more peaceful with each slow breath. Whatever the ultimate fate of the universe, the story we are part of is immeasurably vast and ancient. Whether the universe ends in fire or ice, in sudden catastrophe or gradual fading, the story it has told and continues to tell is one of almost incomprehensible vastness and beauty, a narrative that began perhaps 14 billion years ago with a burst of energy and light, and has unfolded ever since through the formation of galaxies, the burning of stars, the assembly of planets, and the emergence of life and consciousness on at least one small world and perhaps on countless others. We are part of this story, woven into its fabric, made from its materials, shaped by its processes, aware for a brief flickering moment of the immense journey that brought us here and the long journey that still lies ahead. Whatever comes next, this story has happened. It has mattered. The story is real. Every atom in your body was forged in the heart of a dying star, billions of years before you were born. The atoms that make up your body, the carbon in your muscles, the nitrogen in your thoughts, the oxygen that flows through your blood, were not present at the beginning of the universe, but were created later, forged in the nuclear furnaces of massive stars that burned for millions of years before exploding in supernovae that scattered their newly minted elements across the cosmos, seeding the clouds of gas from which our solar system would eventually form. You are literally made of star stuff, assembled from ingredients that were cooked in cosmic fires billions of years before the Earth existed, before the sun ignited, before anything we would recognize as home had even begun to form. The iron in your blood was made in the heart of a collapsing star in the moments before it exploded. You carry the ashes of ancient explosions, stardust breathing and dreaming. The calcium in your bones the iron in your blood, the oxygen you breathe, all are gifts from exploded stars. If you could trace the history of every atom in your body, you would find that each one has a story stretching back billions of years. A journey through collapsing gas clouds and burning stellar cores and violent death throes that sent elements flying across light years of space, until eventually they found their way into the disk of debris orbiting our young sun, condensing into the rocky material that became our planet and eventually becoming part of you. The calcium that gives strength to your bones was made in the cores of giant stars. The iron that colors your blood was forged in supernovae. The oxygen that fills your lungs was created by nuclear fusion deep inside stellar furnaces that burned out long before Earth was born. You are a temporary arrangement of cosmic elements, gifts from stars that died for you to live. Consciousness may be the universe's way of knowing itself, a brief moment when matter contemplates its own existence. Some philosophers and scientists have suggested that consciousness, the subjective awareness that allows you to experience the world and to know that you exist, may be the universe's own way of coming to know itself. Matter arranged in such complex patterns that it becomes capable of reflecting upon its own nature and asking questions about its origins and its fate. In this view, you are not separate from the cosmos, but a part of it, a temporary ripple of awareness in an ocean of being, the universe waking up to look at itself through your eyes and wonder at its own vastness. When you contemplate the end of the universe, you are the universe contemplating itself, matter thinking about matter, the cosmos wondering about its own destiny. You are the universe experiencing wonder, awareness arising from the void. The fact that the universe has produced beings capable of understanding its end is itself a remarkable cosmic achievement. For almost all of its 14 billion-year history, the universe had no one to notice it, no consciousness to appreciate its beauty, no intelligence to understand its workings, just matter and energy flowing according to physical laws, with no observer to ask why or how. But here, on at least one small planet and perhaps on many others, the universe has done something truly remarkable. It has produced beings capable of understanding their own existence and their own eventual ending, creatures who can look up at the night sky and comprehend that the stars will one day die, who can trace the future of the cosmos in equations and contemplate timescales that dwarf their own brief lives. That this has happened at all is astonishing. Understanding emerging from matter. The universe learning to know its own fate. And as we reflect on our place in this grand story, we find meaning not in eternity, but in the moment. The brevity of our lives against cosmic time does not diminish their significance, but rather illuminates it. When set against the vast stretches of cosmic time, the span of a human life seems almost comically brief, a few decades flickering by in what amounts to an instant on the scale of epochs and eons. Yet this brevity does not diminish the significance of our existence, but rather illuminates it. For it is precisely because our time is finite that each moment matters. Precisely because we will not be here forever that our choices and experiences and connections carry weight. A universe that lasted only a moment would be infinitely precious, and a life that lasts only decades is precious for the same reason. The fact that the cosmos will eventually grow dark does not make the light meaningless, but makes it all the more worth cherishing while it shines. Meaning found in transience, preciousness arising from impermanence. Every act of kindness, every moment of connection, every thought and feeling happens against the backdrop of eternity. The small moments that make up a human life, a conversation with a friend, a meal shared with family, a moment of quiet contemplation as you drift towards sleep. All of these happen against the vast backdrop of cosmic time, each one a tiny flame burning briefly in the darkness before the long night ahead. And yet each one is entirely real, entirely significant, entirely worth experiencing and remembering. The universe may grow cold and empty, but it cannot undo the fact that these moments happened, that joy and sorrow and love and wonder were felt by beings made of star stuff on a small blue planet orbiting an ordinary star in an unremarkable corner of an unremarkable galaxy. What happened cannot be unhappened. Every moment is forever etched in the fabric of time. Your feelings are part of cosmic history. The universe may end in silence, but it began in fire, and in between there was love and wonder and life. Whatever the final fate of the cosmos, whether it fades slowly into heat death, or is torn apart in a big rip, or collapses back into a singularity, or cycles endlessly through eons of creation and destruction, the fact remains that in the 14 billion years between the Big Bang and now, remarkable things have happened. Things that the cold equations of physics could never have predicted. Things that arose from the laws of nature but transcended their origins. Stars formed and died, planets coalesced from cosmic dust, oceans filled with water and then with life, and eventually consciousness emerged to look upon it all with wonder. Love was felt, beauty was noticed, and meaning was made by creatures who knew they would not last forever. The ending does not erase the story. Fire, then wonder, then silence. Even if all traces of humanity vanish, the fact that we existed, that we loved and dreamed, will have been true forever. Long after the last human memory has faded through whatever combination of extinction, evolution, or cosmic catastrophe awaits our species, the fact that we existed, that we built cities and wrote poems and fell in love and looked up at the stars wondering what it all meant, will remain eternally true, inscribed not in any physical record, but in the unchangeable past that has already happened and can never be undone. The future may forget us, but it cannot make us not have been. The block of space-time that contains the Earth in the early 21st century, with all its complexity and beauty and suffering, will always be there, even when no observer remains to remember it, a permanent fixture in the structure of reality. We happened. That truth is eternal. Nothing can make us not have been. The stars that will one day fade gave us the light by which we learned to see, to think, to wonder. The very stars that will eventually exhaust their fuel and flicker out into darkness are the same stars that made the heavy elements from which we are constructed, the same stars whose light has illuminated our nights for as long as humans have existed, the same stars that inspired ancient peoples to tell stories and imagine gods, and eventually to build telescopes and discover the true nature of the cosmos. We owe our existence to the mortality of stars, for without their deaths, there would be no oxygen to breathe, no carbon to build our bodies, no iron to carry our blood, and without their light, we would never have developed eyes to see or minds to wonder. The stars are both our ancestors and our teachers, dying to give us life, shining to give us sight. In the face of cosmic endings, we find not despair, but a deeper appreciation for the improbable gift of now. When we truly contemplate the vastness of cosmic time and the inevitability of cosmic endings, the natural response might seem to be despair, a crushing sense of insignificance in the face of forces so much larger and longer than ourselves. Yet many people find exactly the opposite, a deep and abiding appreciation for the improbable gift of existing at all, of being here, now, aware and wondering, in this brief bright window between the Big Bang and the long darkness to come. The fact that the night will eventually come does not diminish the beauty of the day, but makes each moment of light all the more precious. We are impossibly fortunate to exist, to feel, to think, to love, even if only for a little while. Not despair, but gratitude, the gift of this moment. Tonight, as you rest beneath the turning heavens, you are part of the universe's slow journey towards stillness. Right now, as you lie here in the quiet darkness, the universe continues its long journey toward whatever ending awaits. stars burning and cooling, galaxies drifting apart, entropy slowly increasing in every corner of the cosmos. And you are part of this journey, not separate from it, but woven into its fabric. Your atoms borrowed from the cosmic inventory. Your breath part of the great cycling of matter and energy that has been going on since the beginning and will continue until the end. You are the universe resting, the cosmos pausing to gather itself before continuing on, and this moment of peace and stillness is as much a part of the cosmic story as the burning of stars or the merging of galaxies. You are a small, warm presence within this vast unfolding, part of the journey towards silence. And in this quiet moment, in the warmth of your own breath, you carry within you the memory of stars. As you lie here, breathing slowly, feeling the weight of your body against the bed and the gentle heaviness of approaching sleep, you carry within you the memory of stars, atoms that remember being forged in nuclear fires billions of years ago, elements that have journeyed across the cosmos and through countless transformations to arrive here, now assembled into the particular pattern that is you, aware for this brief moment of the vast story of which you are a part. The stars are not separate from you, but within you, their legacy written in your bones and your thoughts, their light continuing in the spark of your consciousness. When you dream tonight, the cosmos dreams, and the memory of starlight drifts with you into sleep. And so our journey through the end of the universe draws softly to a close, leaving behind the vast silences and slow turnings of cosmic time. We have traveled together from the bright age of stars to the cooling embers of white dwarfs, from the patient evaporation of black holes to the infinite stillness of the dark era. We have glimpsed the many ways the universe might end, and found in each of them a strange and distant beauty. These are not endings to fear, but simply the final chapters of a story that began with light and fire, a story of which you are an improbable and wondrous part. If these quiet cosmic journeys help you find rest, consider leaving a like or subscribing to join our growing community of sleepy souls. There are more wonders waiting, more gentle facts to carry you through the night. And perhaps next time, we will explore another corner of the universe together, another soft mystery to guide you towards sleep. Right now, as you lie here in the quiet of your room, the universe continues its slow expansion, carrying galaxies apart, cooling stars, stretching light. The same atoms that will one day drift through the endless dark era are within you now, warm and alive, part of this brief and beautiful moment between the Big Bang and whatever comes after. You are made of the cosmos, and the cosmos rests within you. Let your eyes fall closed if they have not already, and allow your breathing to become slow and even, like the gentle pulse of light from a distant star. Feel your body growing heavy, sinking softly into the bed beneath you, supported and held. Let go of any thoughts that no longer serve you, letting them drift away like photons escaping into the void. There is nothing you need to do now, nothing to solve or remember. Simply rest. Tonight, as you sleep, the universe continues its grand, unhurried journey. Somewhere, a star is being born from a cloud of dust and gas. Somewhere else, a white dwarf is cooling by a fraction of a degree. Black holes are slowly evaporating, galaxies are drifting apart, and the cosmic background radiation is stretching ever longer and fainter. You are a small, warm presence within this vast cosmic story, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you are made of stardust, born from the death of suns, and that your rest tonight is part of the universe's own slow turning towards stillness. This has been Drowsy Discovery. Good night.